Okay, let's see if we have sound. Do we have signal to the camera? We do. Do we have voice through the microphones, through the speakers? We do. We do or we don't? Are these speakers working? Do I need to try something else? So that's a thumbs up. Okay, good. All right, so where are we headed today? What we're going to do today is we're going to continue the story we ended with last time, where we put that crystal of sodium chloride at the bottom of a beaker and asked the question of what the effect of the water would be on that crystal. And we said that if it's a sodium chloride crystal, which dissociates completely in water, that sodium chloride crystal will dissociate into sodium ions and chloride ions. And that if we take 100 millimoles of sodium chloride, that will dissociate into 100 millimoles of sodium and 100 millimoles of chloride. What we're going to do today is we're going to talk about how the ions will diffuse in the water column. So you can imagine last time where we talked about how the ions would leave the crystal and then move into the water column. We're going to talk about the idea of how these ions now are going to move throughout the water column and come to an equilibrium, such that wherever you sample that fluid, it will contain the same concentration of ions, sodium and chloride. We've reached an equilibrium. So we'll walk our way through reaching that equilibrium, and then we're going to talk about the concept of hydrophilic. Those ions are water-loving. Those ions easily associate with the dipole moments on water. So they're hydrophilic. And as such, those hydrophilic molecules are easily soluble in water. And we're going to contrast that with hydrophobic molecules, which don't easily go into solution in water. We know about these. We know intuitively about these molecules. These are molecules like fat, animal fat, and vegetable oils. And we know if we make a salad dressing that we put the oil into the water and it comes out of solution. They're hydrophobic. We'll talk a little bit about the chemistry of those and why, in fact, they are so hydrophobic, why they're so insoluble in water. And if there's time, then we'll finish with the story of amphipathic. The term amphipathic comes from the Greek. It means both feeling. And these both feeling molecules are ones that can live in either a hydrophilic environment or a hydrophobic environment. And we'll see that a classic example of an amphipathic molecule is a phospholipid. It has a phosphate head group that's charged and fatty acid side chains that are uncharged. And we'll talk about how their interaction with water, the interaction of water of phospholipids, gives rise to biological membranes. But first, what we want to do is lay out this idea of ion diffusion, the idea of coming to equilibrium. We're then going to talk about ion diffusion across a barrier, again coming to equilibrium. And then we'll finish with the story of water diffusion across a barrier, which is a particular kind of diffusion called osmosis. And we'll walk our way all through all those. And then hydrophilic versus hydrophobic. When you see the term hydrophilic, immediately glom onto the idea that those molecules are either charged, they have some kind of a charge on them, plus or minus, or they're polar. Molecules that have an end to them that have usually a hydroxyl or free double bonded oxygen, those are polar. Those go into solution in water, so they're hydrophilic. Hydrophobic molecules, on the other hand, the term hydro means water, phobic means fearing. These are water-fearing molecules. They are uncharged. They don't like to go into solution in water. Examples of those are things like triglycerides. We're then going to generate a triglyceride. We're going to tell you a little bit about the chemistry. Now, I'm not going to hold you to the chemistry. I'll never ask you to repeat these structures. But I think it's worthwhile walking through the structure of these molecules, sort of in a stick diagram, so you have a sense of why these molecules are so hydrophobic, how the electrons being equally shared among all the carbons, among all the hydrogens, with the oxygens, that these molecules are hydrophobic because they're largely uncharged. And then we'll finish with these molecules that are neither here nor there. They have both characteristics. They're amphipathic, again from the Greek, meaning both feeling. These phospholipids will have a charged end called a head group. I'll show you some of the structures of that. And they'll have an uncharged region called the fatty acid side chains. So these have both characteristics that are hydrophilic and hydrophobic, and these will be the basis of biological membranes. So we'll spend a lot of time talking about how we're going to construct membranes from these. But let's start where we were yesterday. In fact, let me show you a couple of slides. I hope. That's the first one. Okay. What? It's magic. All right. Okay. So what we're looking at here is a diagram of the water molecule that I put on the board yesterday. And it's trying in this scale drawing to demonstrate the difference in the size of the oxygen molecule and the size of the hydrogen atom. And the hydrogen atom, because it's much smaller, is composed, I think my pointer is not here, okay. The hydrogen atom, shown in blue, is much smaller, and it only is composed of a single proton and an electron. And it's sharing that electron with the oxygen's electrons. And in so doing, though, because the oxygen is so much more massive than the hydrogen, the oxygen has stolen or borrowed those electrons, giving it a dipole moment that's negatively charged in the oxygen end of the molecule and positively charged on the hydrogen end of the molecule. That then gave rise to this pretty picture in the next slide, which shows the dipole moments and the hydrogen bonding, which results from the dipole moments. So you notice that the positive charge in the hydrogen is lined up with the negative charge in the oxygen. And those are the hydrogen bonds, the electromagnetic fields, which are holding those water molecules together. Now, to be sure, water is liquid at room temperature. And so that means the period of time that those bonds exist is very, very short, picoseconds. And then the molecule moves around and forms another hydrogen bond. But that's why water is liquid at room temperature. And if we take enough energy out of it, we'll actually form a crystal called ice. And this is where we left off, basically. We said that we would take a molecule of sodium chloride. Sodium chloride crystals are arranged in a cubic structure, where for each chloride ion, there's a corresponding sodium ion. But because those chloride ions, which are anions, and the sodium ions, which are cations, are so heavily charged, they easily go into solution in water. They easily interact with the dipole moments in water, and so they're highly soluble. And we know this. We know that if you take sodium chloride and dump it into your water glass at dinner, it's going to go into solution. And what they show in the bottom portion of this figure is how the positive ends on the water molecules, the positive dipole moment, is lined up with a negative charge on the chloride. That's an anion. Whereas we flip that round with the positive charge on sodium, where the negative ends, the oxygen ends of the water, are lined up with the positive charges on the sodium, and that forms a spherical shell of hydration around those ions. Let's now go to the board, and then I'll draw out what I want to tell you. Where we left off, and we gave some numbers to this, where we said we had 1 liter of water. And that in the bottom of the beaker, we had placed the sodium chloride. For each of the negatively charged chlorides, there'll be a positively charged sodium, and they're lined up 1-to-1 in that crystal. But when the water molecules are bouncing against these sodium chloride crystals, they'll force the sodium ions and chloride ions to separate from one another so that the sodium goes into solution. And will associate with the negative ends on the water. And chloride, similarly, will interact with the water molecules. Now, initially, the concentration of sodium ions and chloride ions in the immediate vicinity of the sodium chloride crystal will be pretty high. It makes sense. I mean, that's where the sodium chloride is a crystal. The water molecules are bumping into it. And so we'll have a high concentration of sodium chloride right here. But it doesn't take very long before the buffeting, the random walk of the sodium ions and the chlorides in the water will now diffuse or distribute those ions evenly throughout the water column. So it's just a random walk of the ions. As the random walk of the ions distributes those ions evenly through the water column, we reach something called equilibrium. At equilibrium, it doesn't matter where in this solution you take a sample of that fluid. It will have the same concentration of sodium ions and same concentration of chloride ions. It's just the idea of reaching equilibrium, which happens over time because of the random movement of the sodium ions and the chloride ions in the water solution. Well, let's take that idea and expand it a little bit farther. And imagine we have another beaker. But now we divide that beaker into two equal volumes. On the left side, we have 1 liter. And on the right side, we have 1 liter. But the difference here is that on the left side, we have 0.1 molar sodium chloride. You remember from yesterday, this means we'll have 0.1 moles of sodium ion and 0.1 moles of chloride ion, because this sodium chloride crystal is completely dissociated into sodium and chloride ions. Now, as long as this barrier is intact, has no holes in it, then there's no way we can move ions from this side to this side or water from this side to this side either way. But remember, we have just pure water over here. There are no ions in this water, it's just water. And then we're going to put some pathways across this barrier. And some of those pathways with just the right side to permit chloride movement. We'll say this is a chloride channel. Similarly, we're going to have these channels across the membrane, which we'll now label sodium channels. And one more down here for a chloride channel. So now if you imagine these ions as sort of like ping pong pinballs. They're bouncing against the wall. Most of the time they strike the wall and bounce back. They can't get through. But now and again there's a lucky hit. Now and again a chloride ion will find just the right spot and go through the chloride channel. And now and again just the right hit, the sodium ion will go through the channel. Now remember, we have 0.1 moles, 100 millimoles of sodium ions over here, 100 millimoles of chloride ions over here. We have none over here. So if these ions are bouncing against the wall, then the probability of having an ion move to left to right has to be all chloride or all sodium, because that's all we have over here. And initially, the sodium ions move left to right. They walk down their gradient. They move from where they're in high concentration to where they're in low concentration. And the concentration on this side begins to increase. So eventually, though, we reach an equilibrium. where the sodium concentration on the left, and the chloride concentration on the left, reaches 50 millimolar. That's just half of 0.1 molar, so it's 0.05 molar. And that equilibrium was reached. Oh, that's annoying. I don't care if you're starting installation. Okay, fine. It won't go away. Okay. And so what we see at equilibrium is that these ions have moved from left to right. And so now we have gone from 0.1 to 0.5, 0.05, and 0.05. We've reached an equilibrium. Now, think about what's going on at the equilibrium. We now have the same number of ions on the right side as we have on the left. So the probability of an ion moving right to left is the same as the probability of moving left to right. As long as the concentration on the left side is higher than the concentration on the right side, probabilities are such that you're going to move left to right. Randomness is going to carry you down the concentration gradient. But once the concentrations are the same on each side, we have the same number of particles on each side of the barrier, then the probability is the same whether it moves left to right or right to left. There's selectivity for the ions, but there's no selectivity for the direction. So we've reached an equilibrium. We've just moved the ions from a region of higher concentration to a region of lower concentration. So any questions on that? Yes?
I was curious, have you made the channels different? Is it a charge?
Okay, you're questioning the charge. I have ignored the charge here. And you're right. If we were to consider the charge here, then we'd have to be sure that for each time we moved a chloride left to right, we'd better move a sodium left to right. Otherwise, we reach a charge imbalance. And we'll come to that when we talk about the nervous system. We'll talk about membrane potentials, and we'll talk about how we're separating ions across the membrane. And we'll talk about how we can use a differential in charge of ions, particularly the large negative anions which don't move, and the movement of potassium. But let's hold that for a little while, and we start thinking about charge. All I want to think about now here is just the concentration of the ions, okay? But you're right, there will be a charge effect here that I'm ignoring. Yes, and then, yeah.
I think more specifically what she was asking is what makes it specifically a chlorine channel or a sodium channel.
Oh, okay. So the question is, what makes a chloride channel or a sodium channel? That seems to be by the size of the channel. And the physics of this is well known. The biophysics is well known, particularly in biological membranes, where you'll have some channels which are permeable only to sodium, and others which are permeable only to potassium. And that has to do with the size of the ion itself, but also has to do with the hydrated size of the ion. And so what happens in a potassium channel is that all of those waters of hydration are stripped off, and just the potassium channel moves through this just the potassium ion moves through this very narrow part of the channel. And it's so narrow that a sodium ion can't go through. Now, this is a thought experiment. All we did here is put a couple of lines across the membrane, say one allows chloride, one allows sodium. In biology, that's largely done by size, and it's largely done by the waters of hydration. Yes?
So then would the water then move back to stabilize it?
So the question is about water. So let's hold on that, and we're going to come to that.
Sorry.
So the question is water going to move back? Well, we don't have any pathway for water in here. We didn't impose any water channels. So there's no way the water can move.
Okay.
Only the ions can move. But your point's well taken, and that's where we're headed now.
Okay.
What we're going to do now is we're going to set up the same experiment. And instead of having ion channels, we're going to put in another kind of channel called a water channel. We won't be able to move ions, we'll be able to move water. And then we'll ask the question, where's the water going to go? Okay? So let's do that. Yes?
Just to clarify, equilibrium is when there's like the same number of sodium and chloride ions on either side.
Say that again, please.
So is equilibrium when there's like an equal concentration of sodium and chloride ions on either side?
Yes, equilibrium is reached when you have the same number of sodium ions here, same number of sodium ions here, same number of chloride ions here, same number of chloride ions here. If you didn't reach an equilibrium that way, the point that was made earlier is you have a charge difference. Because you have more negative charge on one side and more positive charge on the other side. And we're avoiding that question. We're saying that these ions all have the same permeability. They all have the same probability of moving an ion, so we'll move as much chloride as we move sodium. There's another question. Yes?
Is this a big enough change where you could see a difference in volume before and after?
The question is, will you see a change in volume? Answer is yes. You'll actually see the volume will change, the volume will increase because these ions are going to be taking up space. Absolutely. And that also is going to play into the next story of osmosis. Anything else? Okay, so let's take this panel, and now we're going to do the same kind of arrangement. So that there's our beaker. Here's the barrier. We have water on both sides. Now in this case, we're going to have water on the side. And on this side, what we're going to have is 0.1 moles of chloride and 0.1 moles of sodium. Now, as the question just pointed out, these sodium ions, these chloride ions, are going to be taking up some volume. They're going to be taking up some space. But we're going to say that we have exactly the same volume on both sides. So then across this membrane, we're going to put channels. And these channels are going to be different from the ones on the upper board. These are going to be water-specific channels. In biology, these water-specific channels have a name. They're called aqua porins. So now we've made an arrangement here on our thought experiment where water's on one side, but ions are on this side. And the ions are taking up some room. So on which side of this barrier would the water concentration be higher? It's higher on this side, because we only have water on this side, but we have 0.2 moles of particles on this side. And these 0.2 moles of particles are taking up space. So that means the water concentration, the number of water molecules per given volume, is greater here than here. Now we allow the water molecules to bounce against the wall. The water molecules bounce against the wall, but there are more water molecules on this side than this side. So that means the net flow of water is going to be from this side, from right to left. This water flow down its concentration gradient has a special name called osmosis. Osmosis is pretty important in our world, and we're going to end up talking a whole lot about osmosis when we get to the kidney. But if you go outside today and you look at a tree, that tree is moving water by osmosis. What it's doing is it has a concentration of ions inside its cell, and the water that's free in the soil around the roots is now diffusing into those cells. And it'll diffuse from cell to cell to cell in the water vascular system and carry that water to the top of the tree. But there's a limit on how high you can do that. And you'll see why that is if you look at this for a moment. Because regardless of how much water I have out here, there's always a little bit of salt in here. So the concentration of water on this side of the barrier is always lower than on this side. So there's a constant movement of water in. That's true in the tree as well. But now, if you imagine this, what's going to happen is that as this water moves right to left, this column of water is going to get higher and higher. I have to move my barrier up here. And this water has mass. And so it's going to force a pressure. It's going to force a pressure called a hydrostatic pressure. And theoretically, you can only get a tree so tall because of this. Because you reach a point where the hydrostatic pressure becomes equilibrium with the osmotic pressure, and you can't draw any more water. That limit is, I think, about 100 feet. But we know full well there are trees that are much taller than that. But the trees that are taller than that are things like the redwoods. And the redwoods live in an area always right along the coast. And there's a constant mist coming off the ocean in those areas. And so those trees are adapted not only to move water up through their root systems, but also to take water in through their coniferous leaves directly out of the air. So that's why they can grow so tall. But again, that tells us a little about physiology, but I think it's an interesting illustration of the importance of osmosis and how we can reach an equilibrium between osmotic pressures and hydrostatic pressures. Yes?
How is the pressure created again? I know that you said that the water, when it rises, has mass because of the ions, but what is...
It has mass simply because of the water.
Oh, okay. But what causes the pressure?
What causes the pressure?
Yes.
It's just weight. It's just the mass.
Just the weight between, like in this example, the mass in the cup itself?
It's just the mass of the water on this side of the barrier.
Okay.
So imagine you had a hose, and you had a hose and it had a column of water that was 20 feet high. There'd be a lot of weight in that, and that provides a pressure.
Okay.
It's a downward pressure, which is the hydrostatic pressure.
Okay, that makes sense. Thank you.
Okay? Yes.
Is it almost like the mass of the water makes it like too heavy at some point for it to rise anymore?
The water stops going up at some point because the mass is so great that it offsets and comes to equilibrium with the osmotic pressure. So the pressure moving the water right to left by the osmotic forces, the diffusion forces, is now balanced by the hydrostatic pressure, just the mass of the water pushing down. Okay, anything else? So, yes.
Is the osmotic pressure,
What?
what is like the osmotic pressure?
What is the osmotic pressure? The osmotic pressure is the pressure that's generated by the diffusion of water from the right compartment to the left compartment. And you can get fairly high osmotic pressures. And we'll run into these osmotic pressures again when we particularly talk about the kidneys. Yeah?
I just want some clarification. Was the first example an example of diffusion and this is an example of osmosis?
So the question here is, what's the distinction between diffusion and osmosis? It's a good question. They're really the same thing. In the upper panel, what we're talking about is the diffusion of ions, the diffusion of those particles. But here we're talking about the diffusion of the water molecules. And the diffusion of the water molecules has a separate name. It has a special name in biology called osmosis. So it's just a difference in terminology, but I want you to recognize that in both cases we're talking about diffusion, the random walk of these molecules going from a region of higher concentration to a region of lower concentration. In the upper panel, we're removing ions from a region of higher to lower concentration through those ion selective channels. In the bottom panel, we're moving water from a region of higher concentration to lower concentration through the aquaporin channels. But it's still diffusion. Yeah?
So in the case of osmosis, the equilibrium of water is reached when the hydrostatic pressure equals the osmotic pressure and the net flow of water is equal in both directions?
Exactly. So the point she's making is that, are you telling me that we reach an equilibrium in this case where the hydrostatic pressure forcing the water left to right is now equal to the osmotic pressure moving fluid from right to left? And you're right, there's still going to be some movement back and forth, but the net movement will be equal in both directions. Anything else? Okay, well, up to this point, we've been talking about charged ions. And these charged ions are hydrophilic. Hydro meaning water, comes from the Greek. Philic meaning loving. The same word origin as Philadelphia, the city of brotherly love. That's where this comes from, water loving. And these ions are water loving because they're charged and they can interact with the dipole moments on water. But we can go to the other extreme and talk about hydrophobic. Hydrophobic, again, looking at the Greek root means water fearing. Well, the molecular characteristic of these molecules that are hydrophobic is that these are uncharged or nonpolar. These molecules are clearly charged, but we'll see that there are other molecules that are polar molecules. Like glucose or sucrose that are hydrophilic. And their hydrophilicity arises from the fact that they're polar. But let's take some time and emphasize this concept of hydrophobic. And this is something we know about in our everyday lives. We're all familiar with making a salad dressing. So if you go home today and have lunch and you want to have a salad and you mix up a salad dressing, you pretty much know what you're going to do. You're probably going to take some olive oil and probably mix it with some vinegar, which is mostly water, and shake it up and generate that salad dressing, maybe adding a few spices. But what I want to think about is the relationship of the water in the vinegar and the olive oil. So we'll take our beaker, make it a little fancier. It's going to be a carafe. And in the bottom, we're going to pour some olive oil. Olive oil is a classic vegetable oil. And as such, it is hydrophobic. It's said to be a triglyceride. And then in making the salad dressing, we add water to this. And then we'll shake it. We'll shake and we'll shake and we'll shake that salad dressing until what we have is a kind of slurry. Where in the water, there are these droplets of olive oil. So the droplets of olive oil are distributed through the water. We know that if we take that carafe and put it on the counter, it's only a few minutes before we get a separation of the oil. The oil goes to the top because it's less dense than the water. And the water is found in the bottom. Just a simple illustration to show that no matter how hard we shake that carafe, we can't get those olive oil molecules to easily go into solution in water. And why is it that these olive oil molecules are hydrophobic? To understand why these molecules are hydrophobic, we have to spend a little bit of time with the chemistry. And so we're going to talk about a triglyceride. Now, a triglyceride is made from one molecule of glycerol And it's made from 3 molecules of fatty acid. Let's start with the glycerol. Glycerol has 3 carbons. We're going to call this a 3-carbon alcohol. Remember, carbons have to have 4 bonds. So here's a hydrogen, a hydrogen, a hydrogen, a hydrogen, a hydrogen. And then out here was going to be hydroxyl. Whenever you see in biology hydroxyl, that's said to be an alcohol. This is a 3-carbon alcohol, it has 3 hydroxyls on each, one on each of the carbons, so that's glycerol, 3-carbon alcohol. We're now going to use these 3-carbon alcohols and link them to a fatty acid. Now the fatty acid I'm going to show out here is a C, double bonded O, OH. Then we have this great long string of carbons. Each of the carbons, if this is a saturated fat, will have 2 hydrogens. If it's a monounsaturated fat, someplace along here, there's going to be a double bond, and there'll be only 2 hydrogens. Now, I won't go into a whole lot of detail here. This is a monounsaturated fat. Typically, these hydrogens are on the same side of the molecule. That's called cis. And in some cases, you'll find the hydrogens on the opposite side of the double bond. That's called trans. That makes a trans fat. Trans fats are extremely dangerous. And the reason they're dangerous is we just don't have the enzymes to break them down. But they were a boon to bakers, because what you could do is you could make some sort of cake or a pastry and put it on the shelf. And if you made it with these trans fats, they never went bad, because other biological organisms couldn't break them down. Well, we can't break them down either, so we end up letting them build up on our arteries. So there's no safe level of trans fats. We've tried to eliminate them from all of what we eat, so we have these cis organization of the hydrogen bonds. Now, typically what we'll see here is we'll have a string of carbons that are 16, 18, 20, or 22 carbons long. So we have these extremely long strings of carbons. Now, I haven't drawn all of these in. But what I want you to see here is that on this great long string of carbons, the electrons are equally shared between the carbons and the hydrogens. In this case, they're equally shared between the 2 carbons and the neighboring hydrogens. The only place where we have any polarity in this molecule at all is up here in the double bonded oxygen. And this group, the C double bonded OOH, is said to be a carboxylic acid. That's where the term fatty acid comes from. It's a carboxylic acid. Now, we're going to use this chemistry. And what we're going to do is we're going to take this hydroxyl and this hydroxyl, and we're going to generate HOH. And this process is called a dehydration synthesis. Fundamentally, all we're doing is we're taking water out of the molecule, and we're now replacing the OH here and the OH here with a single bond here. So now we have carbon, oxygen, carbon, double bonded oxygen. Those of you who have had some organic chemistry will recognize this immediately as an ester bond. So now we have generated a covalent bond called an ester bond that links this oxygen of the glycerol with this carbon, the carbonyl carbon of the fatty acid. And we can do this for all 3 of the alcohols. We can take this alcohol, oxygen, another carbonyl carbon, and this great long string of carbons with the hydrogens. Put a double bond, do it here. and so forth till we get to 16, 18, or 20 of them. We can do the same thing on all 3 of these alcohols. So again, down here, we'll take this alcohol, and we'll need some enzymes for this, but we take an enzyme, and then we'll now link this oxygen to this carbon, to this great long string of carbons. Put a double bond here. And so forth. Now, if you take that whole molecule, this triglyceride, and it doesn't matter whether you're talking about olive oil or canola oil or lard, which would have no unsaturated bonds, all of those had these great long chains of carbons. And in those long chains of carbons, all of the electrons are being equally shared. There just isn't any charge because of the equal distribution of the electrons. There's almost no charge out here. Because there's no charge here, the only charge is a little bit of polarity here on the carbonyl oxygen, here, the double bonded oxygen. These molecules are virtually insoluble in water. And the reason they're insoluble in water, the reason they're hydrophobic, is the lack of charge. So now we have these 2 extremes. We have molecules that are hydrophilic, or atoms that are hydrophilic, those ions, or perhaps molecules such as sucrose and glucose that are hydrophilic because they're polar. And then we have at this extreme, these molecules that are hydrophobic, they lack charge. Now the next thing we're going to do is we're going to take this molecule and we're going to modify it a little bit. And by modifying it a little bit, we can now change it from a hydrophobic molecule to an amphipathic molecule. And I'll do that on the back board. So on the back board here, we're going to talk about something known as a phospholipid. As a, should I say an, amphipathic. Molecule. We're going to start with the same structure. We're going to start with glycerol. It's the carbon, the hydrogen, the oxygen, the carbon, the oxygen, hydrogen, carbon. Now we're going to take this carbon, form the ester bond, and we're just basically going to take this to the C double bonded O, that's the carbonyl carbon, plus this long chain of carbons out here. I won't put all the hydrogens on. But the story for this is the same as we have in the upper panel. It's the same idea. And we'll do the same thing for this molecule. Carbon, oxygen, carbon, double bonded oxygen. This is an ester bond. These great long carbons. Long chain of carbons. I'll not put the hydrogens in, but that's all uncharged. So this end of the molecule is uncharged. But now we'll use this hydroxyl on the number 3 carbon in a slightly different way. And rather than forming an ester bond out here to these great long chains of carbons, we're going to now take this carbon, link it to an oxygen, link it to a phosphorus, link it to a double bonded oxygen, to a negatively charged oxygen, to an oxygen here, to something out here called a head group. So rather than having this oxygen now linked to fatty acid, this oxygen now is linked to a phosphate. This phosphate now is in turn linked to a molecule out here. There are 3 possibilities. It could be serine, it could be choline, it could be ethanolamine. Serine and choline are both, choline and ethanolamine are both positively charged. Serine has a slight negative charge on it. But what I want you to see is what we've done by taking this phosphate head group with the negative charge oxygen, this polar oxygen here, and then by adding a serine, a choline, or ethanolamine, we've now changed the structure so that this is now charged. It's now hydrophilic. So what we've done here is we've generated a molecule which has this region which is uncharged and hydrophobic. And this region of the molecule which is hydrophilic. It has both hydrophilic and hydrophobic characteristics, so therefore it's said to be amphipathic. In the last minute, let me do kind of a thought experiment here. You can't do this in reality, but let's do a thought experiment where, again, we're going to take our beaker of water. It has a flat surface on it. This is water, so there's going to be oxygens and hydrogens, hydrogens and oxygens. The oxygens will be negatively charged, the hydrogens will have a slight positive charge on them. And now up here in orange, I want to imagine we have a kind of salt shaker. And in this salt shaker, we have phospholipids. And the shorthand for a phospholipid is to show a circle as the phosphate head group. And to show the fatty acid side chains as a couple of squiggles. So if we can imagine putting some of these, make this a little bigger, this salt shaker, and we put these phospholipids in here. If we could imagine shaking these phospholipids out into the surface of the water, how do you think those phospholipids are going to orient themselves with respect to the water? We have charge on the water molecules here. We have charge on the head group. What they're going to do is they're going to line up like soldiers with their tails pointing away. Because the most favorable state here is to have the head groups, which are mostly positively charged, interacting with the negative ends of the water. And if they're negatively charged, they'll interact with the positive ends of the water. But the tails, which are uncharged, are not going to want to interact with the water itself, so they're going to turn away. And so now we have a monolayer of phospholipids on the surface of the water with the head groups pointing to the water and the tails pointing away. What we'll do tomorrow is we'll imagine what's going to happen when we dunk these underwater, because we're going to have some problems with that. We'll start on that tomorrow.